So, when we're organizing this workshop, my co-organizers initially asked me, hey, Andrew, end of the first day, go give a visionary talk. So until several hours ago, my talk was advertised as visionary talk. But I was preparing for this presentation over the last several days. I tried to think what would be the most useful information to you, and what are the things that you could take back to work on Monday and do something different at your job next Monday. And I thought that we had to set context. Right now, as Peter mentioned, I lead Baidu's AI team, so it's a team of about 1,000 people working on vision, speech, NLP, lots of applications of machine learning. And so what I thought I'd do instead is, instead of taking the shiniest pieces of deep learning that I know, I want to take the lessons that I saw at Baidu that are common to so many different academic areas, as well as applications, autonomous cars, augmented reality, advertising, web search, medical diagnosis. We take what I saw, the common lessons, the simple, powerful ideas that I've seen help drive a lot of machine learning progress at Baidu. And I thought I will share those ideas with you because the patterns I see across a lot of projects, I thought might be the patterns that would be most useful to you as well, whatever you are working on in the next several weeks or months. So one common theme that will appear in this presentation today is that the workflow of organizing machine learning projects feels like parts of it are changing in the era of deep learning. So for example, one of the ideas I'll talk about is bias variance. It's a super old idea, right? And then, many of you, maybe all of you have heard of bias and variance. But in the era of deep learning, I feel like there have been some changes to the way we think about bias and variance. So I want to talk about some of these ideas, which maybe aren't even deep learning per se, but have been slowly shifting as we apply deep learning to more and more of our applications. Okay. Oh, and instead of holding all your questions until the end, if you have a question in the middle, feel free to raise your hand as well. I'm very happy to take questions in the middle, since this is a more maybe informal whiteboard talk. Right? Oh, and also, say hi to all home viewers. Hi. All right. So, one question that I still get asked sometimes is, and kind of Andre alluded to this earlier, a lot of the basic ideas of deep learning have been around for decades. So why are they taking off just now, right? Why is it that deep learning, these neural networks we've all known for maybe decades, why are they working so well now? So I think that the one biggest trend in deep learning is scale. That scale drives deep learning progress. I think Andre mentioned scale of data and scale of computation. And I'll just draw a picture that illustrates that concept maybe a little bit more. Right? So if I plot a figure where on the horizontal axis, I plot the amount of data we have for a problem. And on the vertical axis, we plot performance. Right? So x-axis is the amount of spam data you've collected. Y-axis is how accurately can you classify spam. Then if you apply traditional learning algorithms, right, what we found was that the performance often looks like it starts to plateau after a while. It was as if the older generations of learning algorithms, including support vector, logistic regression, SVMs, was as if they didn't know what to do with all the data that we finally had. And what happened kind of over the last 20 years, last 10 years, was with the rise of the internet, rise of mobile, rise of IoT, whereas the society sort of marched to the right of this curve, right, for many problems, not all problems. And so with all the buzz and all the hype about deep learning, in my opinion, the #1 reason that deep learning algorithms work so well is that if you train what we call a small neural net, maybe you get slightly better performance. If you train a medium-sized neural net, right, maybe you get even better performance. And it's only if you train a large neural net that you could train a model with the capacity to absorb all this data that we don't have access to that allows you to get the best possible performance. And so I feel like this is a trend that we're seeing in many verticals, in many application areas. Couple comments. One is that actually when I draw this picture, some people ask me, well, does this mean a small neural net always dominates a traditional learning algorithm? And the answer is not really. Technically, if you look at the small data regime, if you look at the left end of this plot, right, The relative ordering of these algorithms is not that well defined. It depends on who's more motivated to engineer the features better, right? So if you know, the SVM guy is more motivated to spend more time engineering features, they might beat out the neural network application. But because when you don't have much data, a lot of the knowledge of the algorithm comes from hand engineering, right? But this trend is much more evident in the regime of big data where you just can't hand engineer enough features. And the large neural net combined with a lot of data tends to outperform. So a couple of comments. The implication of this figure is that in order to get the best performance, in order to hit that target, you need two things, right? One is you need to train a very large neural network, or a reasonably large neural network, and you need a large amount of data. And so this in turn has caused pressure to train large neural nets, right? Build large nets, as well as get huge amounts of data. So one of the other interesting trends I've seen is that increasingly, I'm finding that it makes sense to build an AI team as well as build a computer systems team and have the two teams kind of sit next to each other. And the reason I say that is, I guess, so let's see, so when we started, Baidu Research, we set our team that way. Other teams are also organized this way. I think Peter mentioned to me that OpenAI also has a systems team and a machine learning team. And the reason we're starting to organize our teams that way, I think, is that some of the computer systems work we do, right? So we have an HPC team, high performance team, supercomputing team at Baidu. Some of the extremely specialized knowledge in HPC is just incredibly difficult for an AI researcher to learn, right? Some people are super smart. Maybe Jeff Dean is smart enough to learn everything, but it's just difficult for any one human to be sufficiently expert in HPC and sufficiently expert in machine learning. And so we've been finding, and Shubo, actually, one of the co-organizers, is on our HPC team. We've been finding that bringing talent from that knowledge from these multiple sources, multiple communities, allows us to get our best performance. You've heard a lot of fantastic presentations today. I want to draw one other picture, which is, in my mind, this is how I mentally bucket work in deep learning. So this might be a useful categorization, right? When you look at the talk, you can mentally put each talk into one of these buckets I'm about to draw. But I feel like there's a lot of work on, I'm going to call, general DL, general models. And this would be basically what the type of model that Hugo LaRochelle talked about this morning, where you have, really densely connected layers, right? Or I guess FC, right, was the, so there's a huge bucket of models there. And then I think a second bucket is sequence models. So 1D sequences. And this is where I would bucket a lot of the work on RNNs, LSTMs, right, GRUs, some of the attention models, which I guess probably Yosha Benji will talk about tomorrow, or maybe others, maybe Quark as well, I'm not sure, right? But so the 1D sequence models is another huge bucket. The third bucket is the image models. This is really 2D and maybe sometimes 3D, but this is where I would tend to bucket all the work of CNNs, convolutional nets. And then in my mental bucket, then there's a fourth one, which is the other, right? And this includes unsupervised learning, the reinforcement learning, right, as well as lots of other creative ideas being explored in literature. And I still find slow feature analysis, sparse coding, ICA, various models kind of in the other category, super exciting. So it turns out that if you look across industry today, almost all the value today is driven by these three buckets, right? So what I mean is those three buckets of algorithms are, causing us to have much better products, right? Or monetizing very well. It's just incredibly useful for lots of things. In some ways, I think this bucket might be the future of AI, right? So I find unsupervised learning especially super exciting. So I'm actually super excited about this as well. Although I think that if, on Monday you have a job and you're trying to build a product or whatever, the chance of you using something from one of these three buckets will be highest. But I definitely encourage you to contribute to research here as well, right? So I said that trend one, the major trend one of deep learning is scale. This is what I would say is maybe major trend two of two trends. This is not going to go on forever, right? I feel major trend two is the rise of end-to-end deep learning especially for rich outputs. And so end-to-end deep learning, I'll say a little bit more in a second exactly what I mean by that. But the examples I'm going to talk about are all from one of these three buckets, right? General DL, sequence models, image 2D, 3D models. But let's see, it's best illustrated with a few examples. Until recently, a lot of machine learning used to output just raw numbers, you know? So I guess in Richard's example, you have a movie review, right? And then, actually, but I prepared totally different examples. I was editing my examples earlier to be more coherent with the speakers before me. But you have a movie review, and then output the sentiment. You know, is this a positive or a negative movie review? Or you might have an image, right? And then you want to do ImageNet object recognition. You know, so this would be a 0, 1 output. This might be an integer from 1 to 1,000. But so until recently, a lot of machine learning was about outputting a single number, maybe a real number, maybe an integer. And I think the number two major trend that I'm really excited about is end-to-end deep learning algorithms that can output much more complex things than numbers. And so one example that you've seen is image captioning, where instead of taking an image and saying this is a cat, you can now take an image and output, you know, an entire string of text using an RNN to generate that sequence. So I guess what Andre, who spoke just now, I think Oriol Vindal's Xu Wei at Baidu, right? A whole bunch of people have worked on this problem. One of the things that I guess my collaborator Adam Coates will talk about tomorrow, maybe Quark as well, not sure, is speech recognition, where you take as input audio and you directly output, you know, the text transcript. Right? And so when we first proposed using this kind of end-to-end architecture to do speech recognition, this is very controversial. We're building the work of Alex Graves, but the idea of actually putting this in the production speech system was very, very controversial when we first said we wanted to do this. But I think the whole community is coming around to this point of view more recently. Or machine translation, say go from English to French. Right? So Yasaskeva, Quackler, others working on this, a lot of teams now. Or given the parameters, synthesize a brand new image, right? And you saw some examples of image synthesis. So I feel like the second major trend of deep learning that I find very exciting, and I mean, this allowing us to build transformative things that we just couldn't build 3 or 4 years ago, has been this trend toward not just learning algorithms and output not just a number, but it can output very complicated things like a sentence or a caption or a French sentence or image or like the recent WaveNet paper, output audio, right? So I think this is maybe the second major trend. So despite all the excitement about end-to-end deep learning, I think that end-to-end deep learning, sadly, is not the solution to everything. I want to give you some rules of thumb for deciding when to use, what is exactly end-to-end deep learning and when to use it and when not to use it. So we're sort of moving to the second bullet, and we'll go through these. So the trend towards end-to-end deep learning has been this idea that instead of engineering a lot of intermediate representations, maybe you can go directly from your raw input to whatever you want to predict, right? So for example, actually to take this, I'm going to use speech as a recurring example. So for speech recognition, previously one used to go from the audio to hand engineered features like MFCCs or something, and then maybe extract phonemes, right? And then eventually you try to generate the transcript. For those of you that aren't sure what a phoneme is, so if you look at the word, listen to the word cat and the word kick, the k sound, right, is the same sound. And so phonemes are this basic units of sound, such as k as a phoneme, and is hypothesized by linguists to be the basic units of sound. So k, a, t would be maybe the 3 phonemes that make up the word cat, right? So traditional speech systems used to do this, and I think 2011, Lee Deng and Jeff Hinton made a lot of progress in speech recognition by saying we can use deep learning to do this first step, but the end-to-end approach to this would be to say, let's forget about phonemes, let's just have a neural net, right? Input the audio and output the transcript. So it turns out that in some problems, this end-to-end approach, so one end is the input, the other end is the output. So the phrase end-to-end deep learning refers to just having a neural net or like a learning algorithm directly go from input to output. That's what end-to-end means. This end-to-end formula I think it makes for great PR, and it's actually very simple, but it only works sometimes. And actually, maybe I'll just tell you this interesting story. This end-to-end story really upset a lot of people. When we were doing this work, I guess I used to go around and say, I think phonemes are a fantasy of linguists, and we should do away with them. And I still remember there was a meeting at Stanford, and some of you know who it was. There was a linguist kind of yelling at me in public for saying that. So maybe I should not. But we turned out to be right, So. All right. So let's see. But the Achilles heel of a lot of deep learning is that you need tons of label data, right? So if this is your X and that's your Y, then for end-to-end deep learning to work, you need a ton of label, input-output data, X comma Y. So to take an example where one may or may not consider end-to-end deep learning, this is a problem I learned about just last week from Curtis Langlers and Darwin, who's in the audience, I think, imagine you want to use X-ray pictures of your hand in order to predict a child's age, right? So this is a real thing. Doctors actually care to look at an X-ray of a child's hand in order to predict the age of the child. So, boy, let me draw an X-ray image, right? So this is, the child's hand. So these are the bones, right? I guess. This is why I'm not a doctor. Okay, so that's a hand, and you see the bones. And so more traditional algorithm might input an image, and then first, extract the bones. So first figure out, oh, there's a bone here, there's a bone here, there's a bone here, and then maybe measure the length of these bones, right? So already I'm going to say bone lengths. And then maybe have some formula, like some linear regression, average, some simple thing to go from the bone length to estimate the age of the child. Right? So this is a non-end-to-end approach to trying to solve this problem. An end-to-end approach would be to take an image and then run a convnet or whatever and just try to output the age of the child. And I think this is one example of a problem where it's very challenging to get end-to-end deep learning to work because you just don't have enough data. You just don't have enough X-rays of children's hands annotated with their ages. And instead, where we see deep learning coming in is in this step, right? To go from image to figure out where the bones are, use deep learning for that. But the advantage of this non-end-to-end architecture is it allows you to hand engineer in more information about the system, such as how bone lengths map to age, right? Which you can kind of get tables about. There are a lot of examples like this. And I think one of the unfortunate things about deep learning is that, let's see, you can, for suitably sexy values of X and Y, you could almost always train a model and publish a paper, but that doesn't always mean that, is actually a good idea. Peter?
Maybe it's the definition of end-to-end, but you could in principle, people are in the front part knowing what's coming later.
I see, yeah. I see, yeah. I see, yes, that's true, yes. Peter's pointing out that in practice, you could, if this is a fixed function f, right, you could backprop all the way from the age, all the way back to the image. Yeah, that's a good idea, actually. Who was it just now who said you better do it quickly? Yeah. Let me give a couple other examples where it might be harder to backprop all the way through, right? So here's an example. Take self-driving cars. Most teams are using an architecture where you input an image, what's in front of the car, let's say, and then you detect other cars, right? And maybe use the image, detect pedestrians, right? Self-driving cars are obviously more complex than this, right? But then now that you know where the other cars and where the pedestrians are relative to your car, you then have a planning algorithm to then come up with a trajectory, right? And then now that you know what's the trajectory that you want your car to drive through, you could then compute the steering direction, right? Let's say. And so this is actually the architecture that most self-driving car teams are using. And there have been interesting approaches to say, well, I'm going to input an image, and I'll put a steering direction, right? And I think this is an example of where, at least with today's state of technology, I'd be very cautious about this second approach. And I think if you have enough data, the second approach will work. And you could even prove a theorem showing that it will work, I think. But I don't know that anyone today has enough data to make this second approach really, really work well. Right, and I think kind of Peter made a great comment just now, and I think some of these components will be incredibly complicated. Like this could be a path plan of explicit search, and you could actually design a really complicated path plan to generate the trajectory, and your ability to hand code that still has a lot of value. Right, so this is one thing to watch out for. I have seen project teams say, I can get X, I can get Y, I'm going to train deep learning. But unless you actually have the data, some of these things make for great demos if you cherry pick the examples, but it can be challenging to get to work at scale. I should say for self-driving cars, this debate is still open. I'm cautious about this. I don't think this will necessarily fail. I just think the data needed to do this will be really immense. So I'd be very cautious about it and right now. But it might work if you have enough data. One of the themes that comes up in machine learning, or really, if you're working on a machine learning project, one thing that will often come up is you will, develop a learning system, train it, maybe it doesn't work as well as you're hoping yet, and the question is, what do you do next, right? This is a very common part of a machine learning, researcher or machine learning engineer's life, which is, you train a model, doesn't do what you want it to yet, so what do you do next, right? This happens to us all the time. And you face a lot of choices. You could collect more data, maybe you want to train it longer, maybe you want a different neural network architecture, maybe you want to try regularization, maybe a bigger model, throw in some more GPUs. So you have a lot of decisions. And I think that a lot of the skill of a machine learning researcher or machine learning engineer is knowing how to make these decisions, right? And the difference in performance and whether do you train a bigger model or do you try regularization, your skill at picking these decisions will have a huge impact on how rapidly you can make progress on an actual machine learning problem. So I want to talk a bit about bias and variance, since that's one of the most basic concepts in machine learning, and I feel like it's evolving slightly in the era of deep learning. So to use as a motivating example, let's say the goal is to build a human-level speech system, right? Speech recognition system. Okay. So what we would typically do, especially in academia, is we'll get a data set. Here's my data set with a lot of examples, and then we shuffle it, and we randomly split it into 70-30 train tests, or maybe 70% train, 15% dev, and 15% test, right? And some people use the term validation set, but I'm just going to use the dev set, or it stands for development set. It means the same thing as validation set. Okay, so it's pretty common. And so what I encourage you to do, if you aren't already, is to measure the following things. Human level error. So let me illustrate an example. Let's say that on your on your dev set, human level error is 1% error. Let's say that your training set error is let me use 5%, and let's say that your dev set error, really, right? Dev set is a proxy for test set, except you tune to the dev set, right? Is 6% error. Okay, so this is one of the most basics. This is really a step in developing a learning algorithm that I encourage you to do if you aren't already, to figure out what are these three numbers. Because these three numbers really helps in terms of telling you what to do next. So in this example, you see that you're doing much worse than human level performance. And so you see that there's a huge gap here from 1% to 5%. And I'm going to call this, right, the bias of your learning algorithm. And for the statisticians in the room, I'm using the terms bias and variance informally, and it doesn't correspond exactly to the way they're defined in textbooks. But I find these useful concepts for deciding how to make progress on your problem. And so I would say that in this example, you have a high bias classifier. You try training a bigger model, or maybe try training longer. We'll come back to this in a second. For a different example, so this is one example. For a different example, if human level error is 1% and training set error were 2%, right, and depth set error was 6%, then you really have a high variance problem, right, like an overfitting problem. And this really tells you what to do, what to try, right? Try adding regularization, or try early stopping, or even better, we get more data. Right? And then there's also really a third case, which is if you have a 1% human level error, I'm going to say 6% depth set error. Oh, actually, let me say 5% depth set error and 10%, 5% training error and 10% depth set error. And in this case, you have high bias and high variance, right? So I guess, yeah, high bias and high variance, like sucks for you, right? So I feel like that when I talk to applied machine learning teams, there's one really simple workflow that is enough to help you make a lot of decisions about what you should be doing on your machine learning application. And if you're wondering why I'm talking about this and what this has to do with deep learning, I'll come back to this in a second, right? This is changing the era of deep learning. But I feel like there's this, almost a workflow, like almost a flow chart, right? Which is, first ask yourself, is your training error high? Oh, and I hope I'm writing big enough that people can see it. If you have trouble reading, let me know, and I'll read it back out. Right? But first, I tend to ask, are you even doing well in your training set? And if your training error is high, then you have high bias, and so your standard tactics like train a bigger model, just train a bigger neural network, or maybe try training longer. Make sure that your optimization algorithm is doing a good enough job. And then there's also this magical one, which is a new model architecture, which is a hard one, right? Come back to that in a second, okay? And then you kind of keep doing that until you're doing well, at least on your training set. Once you're at least doing well on your training set, so your training error is no longer high, so no, training error is not unacceptably high. We then ask, is your depth error high, right? And if the answer is yes, then, if your depth set error is high, then you have a high variance problem, you have an overfitting problem. And so, the solutions are try to get more data, right? Or add regularization, or try a new model architecture. Right? And then and you kind of keep doing this until your depth set error I guess until both you're doing well on your training set and on your depth set, and then hopefully, right, you're done. So I think one of the nice things about this era of deep learning is that no matter where you're stuck, with modern deep learning tools, we have a clear path for making progress in a way that was not true, or at least was much less true in the era before deep learning, which is, in particular, no matter what your problem is, overfitting or underfitting, really high bias or high variance, or maybe both, right? You always have at least one action you can take, which is bigger model or more data. So you could, in the deep learning era, relative to say the logistic regression era, the SVM era, it feels like we more often have a way out of whatever problem we're stuck in. And so I feel like these days people talk less about bias variance trade-off. You might have heard that term, bias variance trade-off, underfitting versus overfitting. And the reason we talked a lot about that in the past was because a lot of the moves available to us, like tuning regularization, that really traded off bias and variance. So it was like a zero-sum thing, right? And you could improve one, but that makes the other one worse. But in the era of deep learning, really one of the reasons I think deep learning has been so powerful is that the coupling between bias and variance can be weaker, and we now have tools, we now have better tools to reduce bias without increasing variance or reduce variance without increasing bias. And really the big one is really you can always train a bigger model, bigger neural network in a way that was harder to do when you're training logistic regression. You have to come up with more and more features, right? So that was just harder to do. So let's see. One of the, and I'm going to add more to this diagram at the bottom in a second, okay? One of the effects of and by the way, I've been surprised. I mean, honestly, this new model architecture, that's really hard, right? It takes a lot of experience, but even if you aren't super experienced with a variety of deep learning models, the things in the blue boxes, you can often do those, and that will drive a lot of progress, right? But if you have experience with how to tune a ConvNet versus a ResNet versus whatever, by all means try those things as well. Definitely encourage you to keep mastering those as well. But this dumb formula of more data, bigger model, more data is enough to do very well on a lot of problems. Right? So let's see. So bigger model puts pressure on systems, which is why we have a high performance computing team. More data has led to another interesting set of investments. So with I guess a lot of us have always had this insatiable hunger for data. We use crowdsourcing for labeling. We try to come up with all sorts of clever ways to get data. One area that I'm seeing more and more activity in, right? It feels a little bit nascent, but I'm seeing a lot of activity in is automatic data synthesis, right? Let's see. And so here's what I mean. Once upon a time, people used to hand engineer features, and there was a lot of skill in hand engineering the features of, like the SIF or the hog or whatever to feed into SVM. Automatic data synthesis is this little area that is small but feels like it's growing, where there is some hand engineering needed, but I'm seeing quite a lot of progress in multiple problems that is enabled by hand engineering synthetic data in order to feed into the giant maw of your neural network. Right, so let me probably best illustrate it with a couple examples. One of the easy ones is OCR. So let's say you want to train a optical character recognition system. And actually, I've been surprised at Baidu. This has tons of users, actually. This is one of my most useful APIs at Baidu, right? If you imagine firing up Microsoft Word and downloading a random picture off the internet, then choose a random Microsoft Word font, choose a random word in the English dictionary, and just type the English word into Microsoft Word in a random font and paste that on top, like a transparent background on top of a random image off the internet, then you just synthesize a training example for OCR, right? And so this gives you access to essentially unlimited amounts of data. It turns out that the simple idea I just described won't work in its natural form. You actually need to do a lot of tuning to blur the synthesized text of the background, to make sure the color contrast matches your training distribution. So I found that in practice it can be a lot of work to fine-tune how you synthesize data. But I've seen in many verticals, and I'll give a few examples. If you do that engineering work, and sadly it's painful engineering, you could actually get a lot of progress. Actually Tao Wang, who was a student here at Stanford, the effect I saw was he engineered this for months with very little progress, and then suddenly he got the parameters right, and he had huge amounts of data and was able to build one of the best OCR systems in the world at that time. Right? Other examples, speech recognition. Right? One of the most powerful ideas for building an effective speech system is if you take clean audio, like a clean relatively noiseless audio and take random background sounds and just synthesize what that person's voice would sound like in the presence of that background noise, right? And this turns out to work remarkably well. So if you record a lot of car noise, what the inside of your car sounds like, and record a lot of clean audio of someone speaking in a quiet environment, the mathematical operation is actually addition, it's superposition of sound, but you basically add the two waveforms together, and then you get an audio clip that sounds like that person talking in a car, and you feed this to your learning algorithm, and so this has a dramatic effect in terms of amplifying the training set for speech recognition, and has a huge effect, actually, we found it a huge effect on performance. And then also NLP, here's one example, actually done by some Stanford students, which is using end-to-end deep learning to do grammar correction. So input a ungrammatical English sentence, maybe written by a non-native speaker, right? And can you automatically have I guess, attention RNN, input an ungrammatical sentence and correct the grammar, just edit the sentence for me. And it turns out that you can synthesize huge amounts of this type of data automatically. And so that'll be another example where data synthesis works very well. And I think video games in RL, right? Really, one of the, well, let me just games broadly, right? One of the most powerful applications of RL, deep RL these days is video games. And I think if you think supervised learning has an insatiable hunger for data, wait till you work with RL algorithms, right? I think the hunger for data is even greater. But when you play video games, the advantage of that is you can synthesize almost infinite amounts of data to feed this even greater more, right? Even greater need that RL algorithms have. So just one note of caution, data synthesis has a lot of limits. I'll tell you one other story. Let's say you want to recognize cars, right? There are a lot of video games. I need to play more video games. What's a video game with cars in it? Oh, GTA, Grand Theft Auto, right? So there's a bunch of cars in Grand Theft Auto. Why don't we just take pictures of cars from Grand Theft Auto, and you can synthesize lots of cars, lots of orientations there, and paste that, give that as training data. It turns out that's difficult to do because from the human perceptual system, there might be 20 cars in a game, but it looks great to you because you can't tell if there are 20 cars in the game or 1,000 cars in the game, right? And so there are situations where the synthetic data set looks great to you because 20 cars in a video game is plenty, it turns out. You don't need 100 different cars for the human to think it looks realistic. But from the perspective of a learning algorithm, this is a very impoverished, very, very poor data set. So I think it's so a lot to be sorted out for data synthesis. For those of you that work in companies, one practice I would strongly recommend is to have a unified data warehouse, right? So what I mean is that if your teams, if your engineer teams, your research teams are going around trying to accumulate the data from lots of different organizations in your company, that's just going to be a pain. It's going to be slow. So at Baidu, our policy is not your data as a company's data, and if it's user data, it goes into my user data warehouse. We should have a discussion about user access rights, privacy, and who can access what data. But at Baidu, I felt very strongly, so we mandate this data needs to come into one, it's a logical warehouse, right? So it's physically distributed across lots of data centers, but it should be in one system. And what we should discuss is access rights, but what we should not discuss is whether or not to bring together data into as unified a data warehouse as possible. And so this is another practice that I found makes access to data just much smoother and allows teams to drive performance. So really, if your boss asks you, tell them that I said build a unified data warehouse, right? This is... So I want to take the train test, bias variance picture and refine it. It turns out that this idea of a 70-30 split, right, train test or whatever, this was common in machine learning kind of in the past when, frankly, most of us in academia were working on relatively small data sets, right? And so, I don't know, there used to be this thing called the UC Irvine repository for machine learning data sets. By today's, it's amazing resource at the time, but by today's standards, it's quite small. And so you download the data set, shuffle the data set, and you have, train, dev, test, or whatever. In production machine learning today, it's much more common for your train and your test distributions to come from different distributions, right? And this creates new problems and new ways of thinking about bias and variance. So let me talk about that. So actually, here's a concrete example, and this is a real example from Baidu, right? We built a very effective speech recognition system, and then recently, actually quite some time back now, we wanted to launch a new product that uses speech recognition. We wanted a speech-enabled rear view mirror, right? So, if you have a car that doesn't have a built-in GPS unit, right? We wanted, and this is a real product in China, we want to let you take out your rear view mirror and put a new, AI-powered, speech-powered rear view mirror, because it's an easier, like an aftermarket installation. So you can speak to your rearview mirror and say, dear rearview mirror, navigate me to whatever, right? So this is a real product. So how do you build a speech recognition system for this in-car speech-enabled rearview mirror? So this is our status, right? We have, let's call it 50,000 hours of data from speech recognition data from all sorts of places, right? A lot of data we bought, some user data that we have permission to use, but a lot of data collected from all sorts of places, but not your in-car rear view mirror scenario, right? And then our product managers can go around and, through quite a lot of work, for this example, I'm going to say, let's say they collect 10 hours more of data from exactly the rear view mirror scenario, right? So, install this thing in the car, get people to drive around, talk to us, you can collect 10 hours of data from exactly the distribution that you want to test on. So the question is, what do you do now, right? Do you throw this 50,000 hours of data away because it's not from the distribution you want, or can you use it in some way? In the older pre-deep learning days, people used to build very separate models. So it was more common to build one speech model for a rear view mirror, one model for the maps voice query, one model for search, one model. And in the era of deep learning, it's becoming more and more common to just power all the data into one model and let the model sort it out. And so long as your model is big enough, you could usually do this. And if you do if you get the features right, you could usually power all the data into one model and often see gains, but certainly usually not see any losses. But the question is, given this data set, how do you split this into train, def, test, right? So here's one thing you could do, which is call this your training set, call this your def set, and call this your test set, right? Turns out this is a bad idea. I would not do this. And so one of the best practices we've derived is make sure your development set and test sets are from the same distribution. Right? I've been finding that this is one of the tips that really boosts the effectiveness of a machine learning team. So in particular, I would make this the training set, and then of my 10 hours, well, let me expand this a little bit, right? Much smaller data set, maybe 5 hours def, 5 hours of tests. And the reason for this is your team will be working to tune things on the def set, right? And the last thing you want is if they spend 3 months working on the def set and then realize when they finally test it that the test is totally different, a lot of work is wasted. So I think to make an analogy, having different def and test set distributions is a bit like if I tell you, hey everyone, let's go north, right? And then a few hours later, when all of you are in Oakland, I say, where are you? Wait, I want you to be in San Francisco. And you go, what? Why should you tell me to go north? Tell me to go to San Francisco, right? And so I think having def and test sets be from the same distribution is one of the ideas that I found really optimizes the team's efficiency, because the development set, which is what your team is going to be tuning its algorithms to, that is really the problem specification, right? And problem specification tells them to go here, but you actually want them to go there, you're going to waste a lot of effort. And so when possible, having def and test from the same distribution, which it isn't always, there are some caveats, but when it's reasonable to do so, this really improves the team's efficiency. And another thing is, once you specify the def set, that's like your problem specification, right? Once you specify the test set, that's your problem specification. Your team might go and collect more training data, or change the training set, or synthesize more training set. But you shouldn't change the test set if the test set is your problem specification, right? So in practice, what I actually recommend is splitting your training set as follows. Your training set, carve out a small part of this. Let me just say 20 hours of data to form, I'm going to call this the training def set, train-def set. But it's basically a development set that's from the same distribution as your training set. and then you have your depth set and your test set, right? So these are what you actually, from the distribution, you actually care about. And these, you have a training set, 50,000 hours of all sorts of data, and maybe we aren't even entirely sure what data this is, but split off just a small part of this. So I guess this is now, what, 49980 hours and 20 hours. And then here's the generalization of the bias variance concept. Actually, let me use this board. But I have to say, the fact that training and test sets don't match is one of the problems that academia doesn't study much. There's some work on domain adaptation. There is some literature on it. But it turns out that when you train and test on different distributions, sometimes it's just random. It's a little bit luck whether you generalize well to a totally different test set. So that's made it hard to study systematically, which is why I think academia has not studied this particular problem as much as I feel it is important to those of us building production systems. But there is some work, but no very widely deployed solutions yet would be my sense. But so I think our best practice is if you now generalize what I was describing just now to the following, which is measure human level performance, measure your training set performance, measure your training depth performance, measure your depth set performance, and measure your test set performance, right? So now you have kind of 5 numbers. So to take an example, let's say human level is 1% error. And I'm going to use very obvious examples for illustration. If your training set performance is 10%, and this is 10.1%, right? 10.1%, 10.2%, right? In this example, then it's quite clear that you have a huge gap between human level performance and training set performance, and so you have a huge bias, right? And so kind of use the bias fixing types of solutions. And then there's just one example I want to, and so I find that in machine learning, one of the most useful things is to look at the aggregate error of your system, which in this case, is your depth set or your test set error, and then to break down the components to figure out how much of what error comes from where, so you know where to focus your attention. So this accumulation of errors, this difference here, this is maybe 9% bias, which is a lot, so I would work on the bias reduction techniques. This gap here, right, this is kind of really the variance. This gap here is due to your train test distribution mismatch. And this is overfitting of dev. Okay, right. So just to be really concrete, here's an example where you have high train test error mismatch, right? Which is if human level performance is 1%, your training error is 2%, your training depth is 2.1%, and then on your depth set, the error suddenly jumps to 10%, right? So this would, sorry, my x-axis doesn't perfectly line up. But if there was a huge gap here, then I would say you have a huge train test set mismatch problem, okay? And so at this basic level of analysis, what, this formula for machine learning, instead of dev, I would replace this with train dev, right? And then in the rest of this really recipe for machine learning, I would then ask, is your dev error high? If yes, then you have a train test mismatch problem, and there the solution would be to try to get more data that's similar to test set, right? Or maybe data synthesis or data augmentation. Try to tweak your training set to make it look more like your test set. And then there's always this kind of Hail Mary, I guess, which is new architecture, right? And then finally, just to finish this up, there's not that much more. Finally, there's this, and then hopefully if you're done, hopefully your test set error will be good. And if If you're doing well on your depth set, but not your test set, it means you've overfit your depth set, so just get some more depth set data, right? Actually, I'll just write this, I guess. Test set, error, high, right? And if yes, then just get more depth data. Okay, and then done. Sorry if this is not too legible. What I wrote here is, if your depth set error is not high, but your test set error is high, it means you've overfit your depth set, so just get more test set, get more depth set data. Okay? So one of the effects I've seen is bias and variance. It sounds so simple, but it's actually much more difficult to apply in practice than it sounds when I talk about it or on text, right? So some tips. For a lot of problems, just calculate these numbers, and this can help drive your analysis in terms of deciding what to do. Yeah, and I find that it takes surprisingly long to really grok, to really understand bias and variance deeply, but I find that people that understand bias and variance deeply are often able to drive very rapid progress in machine learning applications, right? And I know it's much sexier to show you some cool new network architecture, and I don't know, and this really helps our teams make rapid progress on things. So, you know, there's one thing I kind of snuck in here without making it explicit, which is that in this whole analysis, we were benchmarking against human level performance, right? So there's another trend, another thing that has been different. And again, you know, I'm looking across a lot of projects I've seen in many areas and trying to pull out the common trends. But I find that comparing to human level performance is a much more common theme now than several years ago, right? With I guess Andre being the human level benchmark for ImageNet. And really at Baidu, we compare our speech system to human level performance and try to exceed it and so on. So why is that? It turns out that, so why is human level performance, right, such a common theme in applied deep learning? It turns out that if the x-axis is time, as in, you know, how long you've been working on a project, and the y-axis is accuracy, right? If this is human level performance, you know, like human level accuracy or human level performance on some task, you find that for a lot of projects, your teams will make rapid progress, you know, up until they get to human level performance, and then often it will maybe surpass human level performance a bit, and then progress often gets much harder after that, right? But this is a common pattern I see in a lot of problems. So there are multiple reasons why this is the case. I'm curious, like why do you think this is the case? Any guesses? Yeah. Cool, labels are coming from humans.
The labels are made by the humans itself.
Oh, cool, yep, labels coming from humans. Anything else? No. All right, cool. Anything else? Oh, interesting. Architecture's modeled after human brain. Yeah, I don't know, maybe. I think the distance from neural nets to human brains is very far. So that one I would.
I think that the human capacity these kind of problems may be similar in some cases.
I see, yeah, human capacity, these problems similar. Yeah, kind of. Yeah, all close. Yeah, just. Oh, get bored. I see. That's an interesting one. Right, cool. There's one more, and then I'll just. Oh, be satisfied. Okay, cool. You're satisfied and bored, I guess, on two sides of the coin, I guess. All right, so, sure, go ahead. Oh, it depends on human engine. Yeah, yeah, cool. All right. So let me. I think there are all you know, lots of great answers. I think that there are several good reasons for this type of effect. One of them is that there is, for a lot of problems, there is some theoretical limit of performance, right? If you know, some fraction of data is just noisy. In speech recognition, a lot of audio clips are just noisy. Someone picked up a phone and, you know, they're in a rock concert or something, and it's just impossible to figure out what on earth they were saying, right? Or some images, you know, are just so blurry, it's just impossible to figure out what this is. So there is some upper limit, theoretical limits of performance called the optimal error rate, right? And the Bayesians will call this the Bayes rate, right? But really, there is some theoretical optimum where even if you had the best possible function, with best possible parameters, it cannot do better than that because the input is just noisy and sometimes impossible to label. So it turns out that humans are pretty good at a lot of the tasks we do, not all, but humans are actually pretty good at speech recognition, pretty good at computer vision. And so, by the time you surpass human level accuracy, there might not be a lot of room, right, to go further up. So that's kind of one reason. That's just humans are pretty good. Other reasons, I think a couple people said, right? And it turns out that so long as you're still worse than humans, you have better levers to make progress, right? So while worse than humans, right, have good ways to make progress. And so some of those ways are, right, a couple of you mentioned this, you can get labels from humans. Right? You could also carry out error analysis. And error analysis just means look at your data set, look at the examples your algorithm got wrong, and see if the humans have any insight into why a human thought this is a cat, but your algorithm thought it was a dog, or why a human recognized this utterance correctly, but your system just mistranscribed this. And then I think another reason is that it's easier to estimate bias variance effects. Right? And here's what I mean. So let's see. To take another concrete example, let's say that you're working on some image recognition task. Right? If I tell you that your training error is 8%, and your depth error is 10%, right? Well, should you work on bias reduction techniques, or should you work on variance reduction techniques? It's actually very unclear, right? If I tell you that humans get 7.5%, then you're pretty close on the training set to human, and you would think you have more of a variance problem. If I tell you humans can get 1% error, then you know that even on the training set, you're doing way worse than humans. And so, well, you should build a bigger network or something, right? So this piece of information about where humans are, and I think of humans as a proxy, as an approximation for the Bayes error rate, for the optimal error rate. This piece of information really tells you where you should focus your effort, and therefore increases the efficiency of your team. But once you surpass human level efficiency, I mean, if even humans, got a 30% error, right? Then it's just slightly tougher. So that's just another thing that becomes harder to do, that you no longer have a proxy for estimating the Bayes error rate to decide how to improve performance, right? So there are definitely lots of problems where we surpass human level performance and keep getting better and better. But I find that I find that my life building deep learning applications is often easier until we surpass human level performance, which is much better tools. And after we surpass human level performance, well, actually, if you want the details, what we usually try to do is try to find subsets of data where we still do worse than humans. So let's say, for example, right now we surpass human level performance for speech accuracy, for short audio clips taken out of context. But if we find, for example, we're still way worse than humans on one particular type of accented speech, then even if we're much better than humans in the aggregate, if we find we're much worse than humans on the subset of the data, then all these levers still can apply. But it's kind of an advanced topic, maybe, where you segment the training set and analyze separate subsets of the training set. Yeah?
If you think there's a tool that can take human error rate from 30% down to 1%, maybe you can build that tool.
Yeah.
Can you do that?
I see. Actually, that's a wonderful question. I want to ask a related quiz question to everyone in the audience, and we're going to come back to what Alex just said. Right? So, given everything we just said, I have another quiz for you. Right? I'm going to pose a question write down 4 choices and then ask you to raise your hand to vote what you think is the right answer, okay? So I talked about, how the concept of human level accuracy is useful for driving machine learning progress, right? So how do you define human level performance, right? So here's a very concrete example. I'm spending a lot of time working on AI and healthcare, so a lot of medical examples in my head right now. But let's say that you want to do medical imaging for medical diagnosis. So read medical images, tell your patient a certain disease or not, right? So, so medical example. So my question to you is, how do you define human level performance? Choice A is, a typical human, so a non-doctor, right? Let's say that the error rate at reading a certain type of medical image is 3%, right? Choice B is a typical doctor. Let's say a typical doctor makes 1% error. Or I can find an expert doctor, and let's say an expert doctor makes 0.7% error. Or I can find a team of expert doctors. And what I mean is, if I find a team of expert doctors and have a team look at every image and debate and discuss and have them come to the team's best guess of what's happening to this patient, let's say I can get 0.5% error. So think for a few seconds. I'll ask you to vote by raising your hands. Which of these is the most useful definition of human level error if you want to use this to drive the performance of your algorithms? Okay? So who thinks choice A? Raise your hand. Oh, sure. Don't worry about ease of obtaining this data. Yeah, right. So which is the most useful definition? Choice A, who, anyone? Okay, just a couple people. Choice B, who thinks to use this? Cool, like a fifth. Choice C, expert doctors, another fifth. Choice D, oh, cool, wow, interesting. All right, so, so I'll tell you that I think that for the purpose of driving machine learning progress, I think ignoring the cost of collecting data, which is a great question, I would find this definition the most useful because I think that a lot of what we're trying to use human level performance as a proxy for is the Bayes rate, is really the optimal error rate, right? And really to measure the baseline level of noise in your data. And so, if a team of human doctors can get 0.5%, then you know that the mathematically optimal error rate has got to be 0.5% or maybe even a little bit better. And so for the purpose of using this number to drive all these decisions, such as estimate bias and variance, right? That definition gives you the best, estimate of bias, right? Because you know that the Bayes error rate is 0.5 or lower. In practice, because of the cost of getting labels and so on, in practice, I would fully expect teams to use this definition. And by the way, publishing papers is different than the goal of publishing papers is different than the goal of actually building the best possible product, right? So for the purpose of publishing papers, people like to say, oh, we're better than a human level. So for that, I guess using this definition would be what many people do. And if you're actually trying to collect data, there'll be some tiering where, right, get a typical doctor to label the example. If they aren't sure, hire an expert doctor. If they're still unsure, then find, so for the purpose of data collection, you other processes. But for the mathematical analysis, I would tend to use 0.5 as my definition for that number. Cool. Question in the back? Oh, is it possible the team of expert doctors does worse than a single doctor? I don't know. I had to ask the doctors in the audience. I don't know. All right. All right. Just 2 more pages and I'll wrap up. So one of the reasons I think in the era of deep learning we refer to human level performance much more, frankly, is because for a lot of these tasks we are approaching human level performance, right? So when computer vision accuracy, when I guess maybe to continue this example, right? If when your training set accuracy in computer vision was 30% and your depth error was like 35%, then it didn't really matter if human level performance was 1% or 2% or 3%. It didn't affect your decision that much because you're just so clearly so far from base rate. But now, as really more and more deep learning systems are approaching human levels performance on a lot of these tasks, measuring human level performance actually gives you very useful information to drive decision making. And so honestly, for a lot of the teams I work with, when I meet with them, a very common piece of advice is please go and figure out what is human level performance, and then spend some time to have humans label and get that number, because that number is useful for driving some of these decisions. So just two last things, and then we'll finish. You know, one question I get asked a lot is, what can AI do? Really, what can deep learning do, right? And I guess maybe partially a company, you often, you know, with the rise of AI, I feel like, maybe this is again a company thing. In Silicon Valley, we've developed pretty good workflows for designing products in the desktop era and in the mobile era, right? So with processes like draw a wireframe, the designer draws a wireframe, the product manager draws a wireframe, the designer does the visual design or something, or they work together and then the program implements it. So we have well-defined workflows for how to design, typical apps like the Facebook app or the Snapchat app or whatever. We sort of know how to design. We have workflows established in companies to design stuff like that. In the era of AI, I feel like we don't have good processes yet for designing AI products. So for example, how should a product manager specify, I don't know, a self-driving car? Like how do you specify the product definition? Or how does a product manager specify what level of accuracy is needed for my cat detector? It's like so today in Silicon Valley, with AI working better and better, I find us inventing new processes in order to design AI product, right? Processes that really didn't exist before. But one of the questions I often get asked, partially sometimes they're product people, sometimes they're business people, is what can AI do? Because when a product manager is trying to design a new thing, it's nice we can help them know what they can design, and what they can design, there's no way we can build, right? So I want to give you some rules of thumb that are far from perfect, but that I found useful for thinking about what AI can do. Oh, before I tell you the rules I use, here's one of the rules of thumb that a product manager I know was using, which is he says, assume that AI can do absolutely anything, right? And this actually wasn't terrible. It actually led to some good results. But I want to give you some more nuanced ways of communicating about modern deep learning in these sorts of organizations. One is anything that a typical person can do in less than 1 second, right? And I know this rule is far from perfect. There are a lot of counterexamples to this, but this is one of the rules I found useful, which is that if it's a task that a normal person can do with less than 1 second of thinking, there's a very good chance we could automate it with deep learning. So, given a picture, tell me if the face in this picture is smiling or frowning. You don't need to think for more than a second, so yes, we can build deep learning systems and do that really well, right? Or speech recognition, listen to this audio clip, what did they say? You don't need to think for that long, it's less than a second. So this is really a lot of the perception work in computer vision, speech, that deep learning is working on. This rule of thumb works less well for NLP, I think because humans just take time to read text, but we found right now at Baidu, we have a bunch of product managers looking around for tasks that humans can do in less than 1 second to try to automate them. So this has been highly flawed, but still useful rule of thumb. What's the question?
So, how would that affect the human level evaluation? Would you expect the team of experts to evaluate the result in 1 second?
I see.
Or, I don't know.
Yeah.
A week to get to the result?
Yeah, actually, great question. I feel like a lot of the value of deep learning, a lot of the concrete short-term applications, a lot of them have been trying to automate things that people can do. Really, especially people can do in a very short time. And this feeds into all the advantages, when you're trying to automate something that a human can already do. Right?
1 second relates to speed of labeling data because of crowdsourcing.
Oh, I see. Oh, that's an interesting observation. Oh, if a human can label in less than a second, you can get a lot of data. Yeah, that's an interesting observation. Cool. Yeah. Right. And then I think another one, the other huge bucket of deep learning applications that I've seen create tons of value is predicting outcome of the next in sequence of events, right? But so, if there's something that happens over and over, such as, well, maybe not super inspiring, we show a user an ad, right? That happens a lot. And a user clicks on it or doesn't click on it with tons of data to predict if the user will click on the next ad. Probably the most lucrative application of AI deep learning today. Or, Baidu, we run a food delivery service, so we've seen a lot of data of if you order food from this restaurant to go to this destination at this time of day, how long does it take? We've seen that a ton of times. Very good at predicting if you order food, how long will it take to send this food to you. So I feel like, I don't know, deep learning does so much stuff, so I've struggled a bit to come up with simple rules, explain to product managers, right, how to design around it. I found these two rules useful, even though I know these are clearly highly flawed and there are many, many counterexamples, right? So I think, let's see. So it's an exciting find for deep learning because I think it's letting us do a lot of interesting things. It's also causing us to rethink how we organize our companies, like build a systems team, next an AI team, the workflow for process, for a product. So I think there's a lot of excitement going on. The last thing I want to do is, I found that the number one question I get asked is, how do you build a career in machine learning, right? And I think, when I did a Reddit Ask Me Anything, Reddit AMA, that was one of the questions that was asked. Even today, a few people came up to me and said, I've taken a machine learning course, the machine learning MOOC on Coursera or something else. What advice do you have for building a career in machine learning? I have to admit, I don't have an amazing answer to that, but since I get asked that so often, and because I really want to think what would be the most useful content to you, I thought I'll at least attempt an answer, even though it's maybe not a great one, right? So this is the last thing I had at the start, which is kind of personal advice. I think that I was asking myself this same question like a couple months ago, right? Which is, after you've taken a machine learning course, what's the next step for developing your machine learning career? And at that time, I thought the best thing would be if you attend deep learning school. So Sammy, Peter, and I got together to do this. I hope this is really part of the motivation. And then beyond that, right? What are the things that really help? So Baidu have had, actually, I think all of our organizations have had quite a lot of people want to move from non-machine learning into machine learning. And when I look at the career paths, one common thing is after taking these courses to work on a project by yourself, right? I have a lot of respect for Kaggle. A lot of people actually participate in Kaggle and learn from the blogs there and then become better and better at it. But I want to share with you one other thing that I haven't really shared. Oh, by the way, almost everything I talked about today is new content that I've never presented before, right? So I don't know. So I hope it worked okay. Thank you. Thank you. So I want to share with you really what I think of as a PhD student process, right? Which is, a lot of people, really, when I was teaching full-time at Stanford, a lot of people joined Stanford and asked me, how do I become a machine learning researcher? How do I have my own ideas on how to push the bleeding edge of machine learning? And whether, you're working in robotics or machine learning or something else, right? There's one PhD student process that I find has been incredibly reliable. And I'm going to say it, and you may or may not trust it, but I've seen this work so reliably so many times that I hope you take my word for it, that this process reliably turns non-machine learning researchers into, I think very good machine learning researchers, which is, and there's no magic really, read a lot of papers and work on replicating results. And I think that the human brain is a remarkable device. People often ask me, how do you have new ideas? And I find that if you read enough papers and replicate enough results, you will have new ideas on how to push forward the state of the art, right? I don't know how the human brain works, but I've seen this be an incredibly reliable process. Read enough papers and between 20 and 50 papers later, and it's not one or two, it's more like 20 or maybe 50, you will start to have your own ideas. And this has been, so you see Sammy's nodding his head, this is an incredibly reliable process, right? And then my other piece of advice is, so sometimes people ask me what work in AI is like. And I think some people have this picture that when we work on AI, at Baidu or Google, OpenAI, or whatever, I think some people have this picture of us hanging out in these airy, well-lit rooms with natural plants in the background. And we're all standing in front of a whiteboard discussing the future of humanity, right? And all of you know, working on AI is not like that. Frankly, almost all we do is dirty work, right? So one place that I've seen people get tripped up is when they think work on AI is that future of humanity stuff and shy away from the dirty work. And dirty work means anything from going on the internet and downloading data and cleaning data, or downloading a piece of code and tuning parameters to see what happens, or debugging your stack trace to figure out why this silly thing overflowed, or optimizing the database, or hacking a GPU kernel to make it faster, or reading a paper and struggling to replicate the result. At the end, a lot of what we do comes down to dirty work. And yes, there are moments of inspiration, but I've seen people really stall if they refuse to get into the dirty work. So my advice to you is, and actually another place I've seen people stall is if they only do dirty work. Then you can become great at data cleaning, but not become better and better at having your own moments of inspiration. So one of the most reliable formulas I've seen is really if you do both of these. Dig into the dirty work. Like if your team needs you to do some dirty work, just go and do it. But in parallel, read a lot of papers. And I think the combination of these two is the most reliable formula I've seen for producing great researchers. Right? So I want to close with just one more story about this. And I guess some of you may have heard me talk about the Saturday story, right? But for those of you that want to advance your career in machine learning, next weekend you have a choice, right? Next weekend you can either stay at home and watch TV, or you could do this, right? And it turns out this is much harder, and there are no short-term rewards for doing this, right? If next weekend, I think this weekend you guys are all doing great. But next weekend, if you spend next weekend studying, reading papers, replicating results, there are no short-term rewards. If you go to work the following Monday, your boss doesn't know what you did, your peers didn't know what you did. No one's going to pat you on the back and say, good job, you spent all weekend studying. And realistically, after working really, really hard next weekend, you're not actually that much better. You're barely any better at your job. So there's pretty much no reward for working really, really hard all of next weekend. But I think the secret to advancing your career is this. If you do this not just for one weekend, but do this for weekend after weekend for a year, you will become really good at this. In fact, almost everyone I've worked with at Stanford that was close and became great at this, everyone, actually including me when I was a grad student, we all spent late nights, hunched over like a neural net, tuning hyperparameters, trying to figure out why it wasn't working. And it was that process of doing this not just one weekend, but weekend after weekend that allowed all of us really to our brains' neural networks to learn the patterns that taught us how to do this. So I hope that even after this weekend, you keep on spending the time to keep learning, because I promise that if you do this for long enough, you will become really, really good at deep learning. So just to wrap up, I'm super excited about AI. Been making this analogy that AI is the new electricity, right? And what I mean is that just as 100 years ago, electricity transformed industry after industry, right? Electricity transformed agriculture, manufacturing, transportation, communications. I feel like those of you that are familiar with AI are now in an amazing position to go out and transform not just one industry, but potentially a ton of industries. So I guess at Baidu, I have a fun job trying to transform not just one industry, but multiple industries. But I see that it's very rare in the history of in human history where one person, where someone like you, can gain the skills and do the work to have such a huge impact on society. I think in Silicon Valley, the phrase "change the world" is overused, right? You know, every Stanford undergrad says, "I want to change the world." But for those of you that work in AI, I think that the path from what you do to actually having a big impact on a lot of people and helping a lot of people in transportation, in healthcare, in logistics, in whatever, is actually becoming clearer and clearer. So I hope that all of you will, you know, keep working hard even after this weekend and go do a bunch of cool stuff for humanity. Thank you. Thank you. Thank you. Do we make any announcements, Shubo? We're running super late, so I'll be around later if you want. Okay, so let's break for today and look forward to seeing everyone tomorrow. Thank you.